Good morning. So now we are going to study the third module is called the flexural strength. So moment of resistance of PSC beams. In that moment of resistance of PSC beams. So in this one, first we will take the rectangular section and a T section. So where the neutral axis lies in the flange, because the rectangular section is not having any flange or web. So we'll consider the rectangular section and a T section where the neutral axis is within the flange. So the neutral axis, the depth of the neutral axis is calculated by XU, that you can see here also within the flange, right? So for this the direct formula is therefore the moment of calculation of moment of resistance in the page 59 IS 1343, that is equals to M is equals to FPU into AP in the bracket of D minus 0.42 XU, that you can see in the IS 1343 1980, page number 59. Here you can see the direct formula what they had given. M is equals to FPU into AP in the bracket of D minus 0.42 XU. Directly you can see in the page number 59 of IS 13431980, where the M is equals to moment of resistance of the section. FPU is the ultimate tensile stress in the tendon, and AP is the area of pre-tension tendons. D is equals to effective depth and XU is equals to neutral axis depth. Okay, so here I'll come to the PSC. Okay, here I explained all these things, and some more things are there, that is FP. FP is equal to characteristic strength of the cable, that as given in the question, and FP is the effective pre-stressing stress. After all the losses, FP will consider. Next, there are the two tables. One is table 11 and table 12. So table 11 is for calculating the FPU and XU for the pre-tensioned and the post-tensioned with effective bond, right? Pre-tensioned and post-tensioned with effective bond. Table 12 is for calculating the FPU and XU for the post-tensioned with unbonded tendon. What is bond and what is unbonded, that we will see. So effective bond is nothing but the gap between the cable and the duct. Whatever the duct is there, and there are some cables, the gap between the cable and the duct is filled with a cement slurry. So this gap is filled with a cement slurry or something, then it is called the effective bond. And unbonded is the gap is left as it is called the unbonded tendons, right? So table 11 and table 12 we are going to see. What is table 11? So table 11, so here the conduction at the ultimate limit state for the rectangular beams with the pre-tension tendons or with the post-tensional tendons having the effective bond. So effective bond is there, means that we will use. So before that, first we need to calculate the ratio, that is called the AP into FP into B into D into FCK. AP means area of pre-stressing cable, FP means the characteristic strength, and B is width, and D is the depth, effective depth, and FCK is the characteristic strength of concrete. So if you calculate the ratio you can get in the fractions like this: 0.025 up to 0.04 you will get. So at that time you will get the pre-tension member, means this is the answers of FU into 0.87 FP. FU 0.87 FP you'll get FP is already known, means you can calculate the FPU value from this, and by using the second equation, that is XU by D, by using the fraction, so you can know the value of D and you can calculate the XU by using this. So if the pre-tensioned member means directly value, if the post-tension member with effective bond means you can take this value, right? So this is about the table 11, and the table 12 if the unbonded tendons. Unbonded tendons means the ratio will be same, AP into FP divided by B into D into FCK. So if we'll calculate, and here what we'll take in the unbonded tendon, we'll take the values for L by D. L by D means effective length by effective span by effective depth ratio. First we'll calculate the effective span by effective depth. For example, effective span by effective depth, 5 divided by 1 meter, right? 5 divided by 1 meter means 5 meters is the effective length by effective span by effective depth ratio. For that effective depth and effective span ratio, we'll calculate the value of FPU divided by FP. Here you can see the FPU divided by FP value we need to find out. Similarly, for the effective span by effective depth ratio, if it is 10, 20, 30, whatever it may be, for that we need to calculate the XU by D values of the unbonded tendons, right? If the value is in between of 10 and 20, then you have to interpolate between the values, right? Similarly, the AP into FP into B into D into FCK is the ratio, that is called the modular ratio. One second, I'll just check out. Okay. Next, that is about the table 11 and the table 12. Next, we'll take the flanged section. What is meant by the flanged section? Either it is a T section or a I section. For example, if I take the T section, this is called the section of the T flange, right? Where the first one is the depth of the flange, DF, BF is given. BF is width of the flange, depth of the flange, and the width of the web, BW, and the AP is the area of pre-stressing cable. So where the AP is equals to, here you have to remember AP is equals to AP into APW. AP is equals to APW plus APF, where the APW is the area of the flange, web, area of the flange, APF, right? So here the similar notification is there. The FP is equal to characteristic strength of the cable, and FPU is the ultimate stress in the cable. XC is the depth of neutral axis, and here C1 C2 is the compressive forces, that is C1 is equals to the formula they had given, that you have to remember. C2 the formula they had given, and even the formula for T also they had given. T is equals to FP into AP. So here in the figure you can see the C1, the compressive force due to the FPU and APW, due to the web forces, the compressive force which will generate, that is C1, and due to the flange forces, that is C2. C2 is nothing but the compressive force due to the APF, due to the flange forces, right? Next one, the lever arm. Lever arm is A1, A2. What is A1, A2? One second. What is A1, A2? So A1, here you can see the depth from the center of the cable to the compressive, where the compressive force will generate, that is called the A1 and A2. So A1, A2 we can find out total depth, effective depth minus 0.42 XU in the first case, In the second case, A2 is equals to D minus dF by 2. D minus dF by 2. This is about the lever arm. So next one, there are two cases. One, the case one, the neutral axis lies within the flange. Where the neutral axis lies within the flange, XU value will be lesser than the DF value. The same as a rectangular section means if in the T section or the I section, the XU by D, XU is the lesser than the DF, then it is called the neutral axis lies within the flange. Next, the case 2 is the neutral axis lies within the web. So in the case XU value is greater than the DF value, the area of the cable AP is equals to APW plus APF. That is the equation 1. APW is the area of cable for web. APF is the area of cable for flange. So where we can find the formula for the APF, that is equals to 0.45 FCK BF minus BW in the bracket of DF divided by FP. That is the formula to calculate the APF. So from the equation 1 and 2, from the AP equation and APF equation, we can calculate the value of APW. So next, the moment of resistance formula will change. That is equals to MR is equals to FPU into APW into lever R. Next, AP into FP into lever arm. So the MR is equals to FPU into APW D minus 0.42 XU plus FP into APF D minus DF by 2. The lever arm is, for the first case, it is D minus 0.42 XU. The second case, D minus DF by 2. So if the neutral axis lies in the web. So next one, the reinforcement ratio. That is not a modular ratio. It's called the reinforcement ratio. That is called AP into FP into B into D into FCK will becomes APW into FP into BW into D into FCK. So where if the neutral axis lies within the web, then the formula of the reinforcement ratio will also change with respect to the AP. It will be APW and FP will be same, and B instead of B will take BW, width of the web, and D is the effective depth is same, and FCK will be same. So this is about the flexural strength in that the moment of resistance of PLC beams. So next we will going to solve the problem. Thank you.